we reviewed for VLF and for AMT, CSAMT, MT systems, the influence of the galvanic current component in the system response. We saw that in VLF, the galvanic current component virtually dominated the response. Vortex currents played a very, very small role, and our interpretation of VLF would therefore have to be based on galvanic current flow. And this meant that any papers that we found in the literature which discussed targets in free space simply aren't appropriate to the real world. You have to go to the, I might add, usually somewhat more complicated, but not too bad papers which treat the targets in the Earth itself. We then went to the plane wave systems that are operating at lower frequencies, AMT, MT, and we learned there that the role of galvanic current flow was deleterious in the sense that it made our interpretation of the geoelectric section for which we seek with those systems, it made it much more difficult. And basically what it did was to disguise the presence of the layered Earth and added a lot of anomalies which appeared to be at depth, but which were in reality caused by near surface conductivity inhomogeneities. So we'll continue on again this morning, and I was just starting to discuss time domain or large loop systems last night, and before doing it, I'll just quickly review the sort of system that I'm going to be talking about for those of you who may not have had much experience. In the old days, large loop systems operated in either the frequency or the time domain, but for a variety of reasons, the frequency domain is simply not used in this configuration very much, so I'm going to restrict my attention to time domain EM. And as many of you well know, to do large loop surveys, we put out a loop, typically a few hundred meters on a side. If we're moving the loop, as you often do with SIROTEM, for each measurement you might have it 100 or 200 meters on the side. More common in North America, we lay out a large loop and just move the receiver. More on that in a second. And in that case, the transmitter loop can be 300 or 400 meters, even 500 meters in this dimension, and this one here can be up to 1,000 meters. These are large loops. In the North American system, where we use the fixed loop, we then do surveys by moving the receiver along survey lines oriented perpendicular to the long side of the transmitter. I've actually drawn it square, but that one is usually longer than this. And basically, the measurement is done as follows. The current in the large loop, Alex showed this to you yesterday, as a function of time, is usually a truncated square wave. Quarter period it's on, quarter period it's off, quarter period it's on in the opposite direction, quarter period it's off again. The current level's typical, a few amps to 30, 40 amps in large systems. Now, the primary field from this, the primary magnetic field from this current flow, again, as Alex showed you yesterday, will look exactly the same. So the primary field, which is intersecting the target here, note for the moment that I'm ignoring the half space. This target is in free space. The primary magnetic field looks like that. As a result of Faraday's law, at the instance that the transmitter current, and thus the primary magnetic field, change with time, a voltage or EMF is induced in the target, EMF, and the nature of the EMF from Faraday's law is minus d phi by dt. So since I've shown here virtually a square wave with short ramps, the EMF in the target will consist of little pulses, as I've shown, of width equal to the turn-off time. These little pulses of voltage drive a current in the target, We approximate the target, again, as Alex did yesterday, with a resistance and an inductance. We don't get capacitances in EM, in inductive EM, but we do get resistance and inductance. The fact that we have both means that when we hit the target with this little pulse, a current flows which decays with a characteristic time constant of the form e to the minus t over tau, where tau, as I'm sure you well know, is given by the ratio of the inductance to the resistance. To measure the decay characteristics of this target, and that's what we want, because the decay characteristics are going to tell us about the conductivity of the target, we simply have a receiver which has a number of little gates, and we make measurements of the decay at successive times, and since the pulse repeats and repeats and repeats, we stack those measurements up for typically a few seconds, perhaps half a minute, and that's our measurement. A measurement at one receiver location consists usually of 10 or 20 pieces of information, and they are the decay at successive points in time. One other point, the transmitter only does useful work for us when it turns on or off. During the whole rest of the time, it's just out there gathering dust, as it were. However, when it's on, the transmitter current's usually not particularly stable, especially to the part per million levels that we're talking about. So again, as you all know, I suspect, we do measurements only after the transmitter has turned off. In other words, there and there, but not there and not there. Okay, the simple case which I've shown here shows vortex current flow only, but as I started to show you last night, if the ground is conductive, the vortex EMF which is induced in the ground will also cause current flow, and exactly the same way as for the VLF case or the CSAMT case, those currents which normally would flow in circles around the transmitter after I've shut it off will be sucked into the target, and they will also give a magnetic field response. Somebody asked last night, what's the difference between the magnetic field responses from vortex currents and galvanic current flow? And I'm not sure if you understood my answer or not, perhaps some didn't. In the case of vortex currents, the response can be thought, this is probably one of the best kept secrets in EM. If we have a large loop like this, we can often break up we can in general break up the response of this large loop into the response from a number of dipoles. We can add the response from a number of dipoles whose strength is adjusted to give the net result of the large loop that I've shown here. So if that's the case, the response from this loop might be thought of as being from a line of dipoles, and the field from a line of dipoles in general falls off as 1 over r squared. You remember a single dipole, Alex showed you yesterday, falls off as 1 over r cubed. A line of dipoles, 1 over r squared. So the magnetic field might look like that, and the vertical component might look like that. From galvanic current flow, we just have axial current flow like that. Now the magnetic field from a line source of current is a big circle like that. The field falls off as 1 over r, and so the response will be smeared out more in space. So in theory, we should be able to tell the difference between them from the spatial distribution of the response. In fact, it's rather difficult to do. Okay, what I've just told you, how many people have heard this for the first time just now or last night? Can you put up your hands just so I... Okay. To most of you, you know then about time domain EM as I've described it here. Yes? Hands? Okay, good. Okay, thank you for that. We'll get on with the... Okay, so I went through this again last night. No need to repeat it. But what I started to tell you about was a series of calculations that we did to see the relative amplitude of the vortex current response and the galvanic current component response. And this is very, very important in Australia, where you have either a conductive overburden or a conductive half space itself. You'll see that it makes quite a difference to the response. So the calculations that we did, we took a plate target, a large plate, 200 by 600 meters, and we let it have various conductances. The conductance is the conductivity thickness of the plate, and it's a measure basically of how conductive it is. The half space resistivity, as you'll see, we also let vary between 10 and 1,000 ohm meters. 1,000 ohm meters, a very resistive half space, 10 ohm meters, pretty conductive. Our transmitter was a large circular loop for ease of calculation. And what I'm going to show you plots of are plots of the horizontal magnetic field, or more accurately, its time derivative. Why do I do the horizontal magnetic field? Because it's a maximum right over the plate, and it's an easy concept to visualize. The response is going to consist of three components, okay? And I linearly add them. That's an approximation. It's valid at some points in time, at some regions of time. It gives you a good feel for what's going on and some ability to interpret. But these are approximate calculations, and you have to keep that in mind. So we're going to get three responses in this receiver coil, and I'm going to show you the time behavior of those responses. The first one is going to be the response to the plate essentially in free space. And I'm going to show you log-log plots. So here you're going to have log time. Here you're going to have log bx dot. And it turns out that an exponential response on log-log paper looks like this. Okay? You probably remember that on log-lin paper it's a straight line. On log-log it looks like that. I'm going to use plates of three conductances. I think they're 30, 100, and 300 Siemens. That's a very conductive plate. That's a pretty conductive plate. In time domain, and we'll discuss this later, the response is actually 1 over tau e to the minus t over tau in late times, and I'm assuming late times. And that means that in addition to the exponential factor, the initial amplitude of the response is also governed by the time constant. I'll discuss that more in a day or so. But basically what that means is that a plate that has very good conductance, very long time constant, has low initial amplitude and decays slowly. A plate which is less conductive is going to look like that, and a plate which is less conductant, has less conductance still, is going to look like that. So basically, this represents the response from three plates. This one is less conductive, and this one is most conductive. And the reason for that behavior is because of the 1 over tau out in front. No problems? Okay, so that's the first component of the response. The second component of the response is going to be that from the half space itself. I will discuss that more in a day or so again, but basically, for the regions of time which we're interested, again a log-log plot, the fall off of the field is a power law, generally, of the order, and it depends which component we're measuring, but of the order of t to the minus 5 halves. At any rate, a power law at later times Alex will discuss this in much more detail, so it's going to look like a straight line. And the last component which we're going to discuss then is our galvanic current component, and we're going to see that it's rather different from either of these two. And I'll go on now to the next slide and show you what these responses look like. Okay, here's my first plot. This one is done for a 1,000 ohm meter half space, very resistive. We don't expect to see too much problems arising from either the contribution from the Earth or the galvanic current component. And in these slides, I show only the galvanic and the vortex component. You can forget, for the time being, the contribution from the half space itself. Okay, so here's my log time, here's my log response, and here are the three vortex current responses that I showed you from my plates 30 to 300 Siemens. Here, incidentally, is about the level of the system noise. We see that right over the target that the component from the galvanic current flow through the target, and therefore the spatial response of this signal will look roughly like the spatial response from the vortex current component. We see that even in this resistive country, at early times, that the response from the target is actually from the galvanic current component. At later times, no problem at all seeing the vortex current component, and we're greatly relieved to learn that, because we know from my remarks yesterday that most of our interpretive material comes from vortex current flow. We can see target orientation, target depth extent, dip strike, and that sort of thing. So if you don't like the Australian environment, come to Canada, where you get 1,000 ohm meters fairly regularly, and where initially in your decays you'll see a galvanic current component, but as time progresses you will have no trouble in general seeing the vortex current component. Things get a little rougher when you get down to 100 ohm meters. In this case, these target responses from vortex currents stay unchanged, but now we see that the galvanic current component has moved this way in time, and we see that for the 30 Siemens plate, which is still a fairly conductive plate, that the galvanic current component is often much larger, an order of magnitude at early times. We see that at intermediate times they're roughly comparable. At late times, again, the galvanic current component predominates. If we are lucky enough to be looking for more conductive targets, the situation is improved, because the window during which time vortex current predominates is much larger, and we can measure the vortex current flow for this time period here. Incidentally, we would normally take the data and plot it on a log linear plot to look for a straight line on log linear plot to see that we do in fact have vortex current flow. We get down to 10 ohm meter ground, all hell breaks loose. Now we see that the galvanic current component predominates. No way we'll see 30 Siemens plate with vortex currents. No way we'll see it with 100 Siemens, and only at very late times, the order 30, 40 milliseconds, and this is the kind of times that you're used to working out to in Australia. Only at those times do we have a hope of seeing it as a result of vortex current flow. We note now that the ground is so conductive that the galvanic current component is actually different, slightly different, for each of the three plates. Not significantly. In general, you just get a lot of galvanic current component. Basically, you're seeing the targets as a result of line current flowing through them. Okay, so with time TDEM exploration, we see what I've already discussed. The interpretability is reduced. Galvanic current component also affects soundings. And this is an example of a sounding which has been distorted as a result of that current component. This is a central loop sounding. Here's the transmitter, 75 meters on a side. The receiver is located in the center. And what's happened is that the surveyor has set up his loop fairly close to a pipe. And the problem is pipes are, of course, long, have very small cross-sectional area, so we don't expect to get any vortex current flow out of the pipe, but we do expect to get galvanic current component, and in fact, that's what happens. I show here the soundings, apparent resistivity as a function of time for various distances. The apparent resistivity, a concept we'll discuss later, but it's basically a measure of the response as a function of time. When the distance to the pipe is of the order of the intercoil spacing, we see that the soundings as a function of time are not affected by the pipe. There's the sounding for 91 meters, there's the sounding for 64 meters, but once we start getting closer to the pipe, the soundings are seriously distorted. And if you're doing soundings, you have to be very, very careful that there are no nearby conductors. Some people try doing soundings near ore bodies. That's a no-no because you get huge response from the ore bodies. But even small pipes about which you know nothing can give you serious problems.
When that was the square root of time, what was the...
Say again?
Your x-axis was the square root of time then?
Yeah, it was the log of square root of time. We do that. We often plot square root of time because, as we'll see later, the currents in the ground after we shut off the transmitter progress downwards with the square root of time. And so a plot of log root of time very coarsely is log of depth. It's like plotting skin depth, basically. Okay?
They're concepts that were unfamiliar to me.
Yeah, good. Okay, and so they should be, at least as far as we're concerned. We'll discuss them in more detail, quite a lot more detail later on. I just wanted to show in that last slide that the data was not good as a result of the pipe, without going into too many details as to. Okay, I think you're probably mostly familiar with horizontal loop EM. I'm not sure. How many of you are familiar with moving horizontal loop systems? Right hands up. Somewhat familiar? Okay. Basically, here I have a transmitter. Here I have a receiver, usually working now in the frequency domain. And these systems are used, particularly in North America, where the ground tends to be more resistive. They're used for looking for base metal targets, metallic sulfides, that sort of thing. Typically, the intercoil spacing would be 100, 200 meters, frequency of operation a few hundred hertz to a few kilohertz, one guy with a transmitter, one guy with the receiver, and vertical plate targets. Vertical plate targets, here's the transmitter, here's the receiver, here's our massive sulfide. Vertical plate targets give us a response which looks like this. This is the in-phase component. That comes from the vortex currents which are in phase with the transmitter current. A classical sling ram anomaly. The quadrature phase component looking much the same, in this case somewhat larger peak-to-peak amplitude, but it's also offset because the quadrature component is more sensitive to the conductivity of the ground. And in this case, the ground is conductive or the overburden is conductive, and the quad phase response has been lifted up. In exactly the same way as before, we have two components to our response. One is from the time-varying magnetic field inducing eddy currents from the target itself, but this transmitter also gives us an electric field in the ground. It's a little hard to see from the figure. Again, it will be concentric circles about the transmitter. And so we're also going to get a galvanic current component. I won't spend too much time on these diagrams. They're done by Jim Hannison. If you want to learn all about them, Neil Hannison. And they show how the response of the target, this is called an Argand diagram, how the response varies as we vary the conductivity in essence of the homogeneous half space. This is a standard Argand diagram. It gives the in-phase and the quadrature phase responses, as points out here, as a function of conductivity of the target and of the depth of the target. Homogeneous half space of zero conductivity gives us our standard diagram. As we start to increase the conductivity of the half space, we start to introduce a significant amount of galvanic current component. We also phase shift the vortex current flow, and you'll see that changing. The whole diagram started to rotate counterclockwise. As the ground gets more and more conductive, it starts to rotate clockwise again, until finally, as the ground gets very conductive, the signals have become much smaller and the phases are completely altered as a result of galvanic current component. Whoops. I think we just lost our...
You want to change to the other path?
Oh, I'm sorry, yes. Alex, 3 more minutes? Just a little warning to start doing your push-ups. Used for sounding, not often, but somewhat, simply by, that is geoelectric sounding, simply by using the fact that the transmitter can be operated at several frequencies. So to do a geoelectric sounding, you simply put the transmitter and the receiver in one place over the area where you want to do your sounding, and you make measurements of the in-phase and quad-phase components of the receiver voltage at different transmitter frequencies. All soundings, in essence, work out to doing that in the frequency domain. There's a problem with the galvanic current component, and I'll discuss that now. Suppose, for the sake of argument, that we just have a conductive overburden. And I show here the transmitter and the receiver. I show the primary magnetic field, and I show the current flow in the overburden. Here I show a plan view of it. Here it is in section. And I show here the currents coming out of the page. And here they're going into the page. Now, it's not widely realized that the man making the magnetic field measurement with the receiver, or d phi dt, dB dt, is measuring the magnetic response from all of these current loops. The magnetic field through the Biot-Savart law is the sum of the responses from each of these current loops. If you look at it, you'll realize that if this is the transmitter, that the magnetic field at the receiver from all of the inside current loops, that is the current loops between the transmitter and the receiver, are in one direction. The magnetic field from all the currents outside are in the other direction. So what the guy with the receiver is actually measuring is the difference between these two magnetic field components. He doesn't know that. He doesn't know that it's the difference between two relatively large and of opposite polarity components. He measures his magnetic field and off he goes. A problem occurs, however, if you have a conductive keel to the overburden. In that case, I've very schematically shown how the currents will be deformed as a result of the conductive keel. And you see that what's happened is that the currents that were out here have essentially disappeared. They're now flowing more or less through the conductive keel. And the net result is that the careful balance between those two components has been destroyed, and you're going to get a large signal or a large change in signal caused by what might be a relatively insignificant keel in the overburden or long thin conductor in the ground. And here I show some calculations from Geophysics, Villegas Garcias and West, from modeling studies done with a sling ram system. Basically a 200-meter intercoil spacing. Here's their conductive overburden, and here's their conductive keel. And they modeled that just by gluing sheets of lead onto the bottom of a big sheet of lead. Here are their responses. Note that the condition for this type of response is that the lateral dimension of this inhomogeneity has to be less than the intercoil spacing. Once that's achieved, it doesn't take much of a thickening of the overburden to give you huge changes in the response. And the problem is that as you do soundings, the skin depth in the ground is changing laterally as you go to higher frequencies, and the contribution from this conductive keel will be a function of frequency. And so it's apt to play hob with your soundings. Yeah?
Is that showing the phase of the quadrature response?
This is showing the in-phase responses and the quadrature phase responses, okay? The quad phase responses are the dashed lines, and the in-phase responses are the solid lines. Good. Thanks. Okay, so that's a problem with soundings. It's a problem with EM prospecting in general with the sling ram systems, because you can get what look like nice bedrock conductors which are caused simply by changes in overburden thickness. Second last slide, I show here an example done with, again, one of these systems. It's actually a conductivity meter of ours. The geology is as follows. We have Lockport dolomite bedrock, very, very resistive, 10,000, 20,000 millimeters, fractured, however, and overlain by a layer of a few meters of lacustrine clay, fairly conductive. So basically we expect two things at the fractures. The material within the fractures themselves may be conductive, but for sure there's differential weathering where the fractures occur, and so we expect to get overburden keels of the sort that I showed you earlier. Here's a VLF survey over the area. In VLF, we're interested in the crossovers of the tilt angle. They show where these structures are, either the faults or the depressions. We phrase or filter the data to make the location of these things more obvious. There they are there, and you'll see that I've sketched them in where the data shows they should be. I go over the survey site with a vertical dipole system. Could be a max min, it's a 34. And look at the data. This is the quadrature phase data along the survey line, and it is truly a dog's breakfast. It's just going up and down. It's going up and down within a few meters. The intercoil spacing here was 20 meters. If I moved 1 meter, I could get a factor of 3 change in the meter reading. As soon as I turned the coils over on the side like this, the readings quieten right down. The only noise left here is still some contribution from this, because I didn't have the coils perfectly vertical, the planes of the coils. And now you can see the response is nice and smooth, and basically it's showing me where the overburden is thickest and where it's thinnest. But the point here is that the presence of this kind of anomaly can be very, very serious in this mode of operation. You'll run into that in Australia when you use your Cyrothem in the offset mode, or Geonics or anybody else's time domain equipment, because this form of current gathering is still present, of course. Frequency or time domain makes no difference. And you'll find sometimes that if you go from central loop mode to the offset mode, that the data gets very noisy. It may not be due to basement conductors. It may be due to changes in the near surface material. You'll have to be in your guard. Okay, I think that that's it. We'll put Alex on. I have here at the end a table of the purported advantages and disadvantages of galvanic current component. Like all tables, it's not particularly useful. But if we look at, in general, the overall effects of galvanic current component, the advantages are that, in general, it lets us see deeper because the linear current filament gives a magnetic field which falls off more slowly with distance, lets us see deeper, lets us see targets further away from the transmitter, but otherwise can get us into a great deal of trouble. So we can't forget it. Alex, your turn.
Do we have a question or two?
Oh, yes, sure, I'm sorry.
That keel thing interests me considerably. If you were to use different separations, you said that when you have a keel, it's worst when your separation, the receiver to transmitter, is
larger than the keel extent.
larger than the keel.
Yeah. If the spacing is much less than the width of the target, you just see an increase in response as you go over the target because of the increased conductivity, and you'd recognize it for what it is. The problem is when the intercoil spacing gets large compared to the target, you don't see a nice response like that. You see a standard bedrock conductor response, and you're in trouble. Okay, I'm sorry, go on with your question.
That was a question. Should we be taking various separations to try to distinguish these near surface responses?
Yeah, if you think you have one, you know, your survey objectives, and we'll discuss this.
Should we routinely be taking two separations?
It's something that you should consider. If you do central loop measurements, as you often do with in Australia with your Cyrotems or 37s or whatever, you avoid this effect, okay? There are other problems with it, but that's not one of them. If you go outside of the loop, then you invite this sort of effect. If you're going to make measurements at two different spacings, I would advise that one of them be 0. In other words, get run back into the transmitter.
Certainly.
Yeah.
And should also, you'd seen that if you took the horizontal component, i.e. vertically orientated.
Yeah. The trouble is you have to turn the transmitter on its side. If you have the transmitter like that, that effect will be in any one of the receiver. Well, there are only two that count, that and that receiver component. The reason it disappeared for that bottom slide was because with the EM34 I can turn the transmitter on its side, and then you don't have this careful balance, it turns out.
How does the horizontal, if you were to take a Z and the X component, how would that null the response from the keel?
If you mean if I do that?
No, you
Do that? Yeah, I could do that, but that's a hell of a way of doing a survey in general because you don't get any response from most of the targets, no half space, no nothing. So your options are really that and that. This is the transmitter, that's the receiver. And both of them are equally sensitive to it. So you just have to learn, you have to learn that it's there. It will have different decay characteristics, for example, because it is an overburden or a half-space effect, so you could detect it that way, for example. Okay? Another way would be doing this, but that really adds up the time to do your survey. So my recommendation would be look at the decay law. That's not always in Australia the good thing that we'd hope it was, but yeah.
Talk about variation in depth of the conductive overburden and the effects that has. What about variation in topography? Would that have a similar effect?
Yes, it can. If you're talking about a frequency domain system again, principally as you know, you have troubles with topography to start with, just trying to get the in-phase component. In general, with a time domain system, if your overburden is uniform, topography itself will not give you a significant response. Yeah. That's one of the advantages of it. That's a big advantage of time domain. Okay, just before I give it over to Alex, how many of you are reasonably confident that you understand what I was talking about? And be modest, don't, it's important that we know roughly what level we should be describing these things at. Pretty new? Pretty new. Okay. Pretty new? Pretty new? Older? Okay. Alex?
We assume there is our body, very peculiar shape, conducting ring. It turns out it's excellent model for understanding and for first approximation. So our goal is to solve the forward problem. What does it mean to solve the forward problem? We take our body, as we assume we know conductivity, we know the shape, we know dimension, and we know where it's located. We know a lot. Now we ask ourselves, what is the field which this our body creates at the points where we measure? That solution, the forward problem, gravity, magnetic, electrical, electromagnetic, seismic, where geophysics, this is the solution of the forward problem. What is the solution of inverse problem? We know field, and we would like to find out what created this field. Where is this body? Where it's located? Where its shape? Where its dimension? How we can do? Only if we compare our results of observations with results of solution of forward problem. That's the straightforward way which is mainly used. So I assume for simplicity that our body in a conducting ring. If you remember, let me remind you how everything happens here. Current in transmitter, some function of time creates what? Primary magnetic field. This primary magnetic field everywhere. Also, since it's a primary magnetic field, which changes with time, it creates what? Inductive electrical field. No charges, inductive. Second cause. So, as this electrical field is hungry, it's looking for ions or electrons. We satisfy its requirement and put here electrons. So, primary electrical field causes motion of the current in this ring. Correct? That's physics. Current arises, its in own turn creates secondary magnetic field, which also changes with time. Therefore, secondary electrical field arises. Clear? So we have two electrical fields. And current which is flowing in this ring is due to primary electrical field and secondary electrical field. Now, if we knew current, can we solve forward problem? Easily. We have to use Biot-Savart law. You see, I'm old teacher, I repeat the same, because that's what I do all time in my practice, not only as a teacher, as geophysicist. One victim is here many years ago, yes, but well, it's mutual. So don't work with equations before you don't understand physical law, what is going on. Then later it could be equations and result. So our goal to find current. When I say to find induced current, I say to solve forward problem practically. So amazing simplicity of this model amazing simplicity, allows us to solve in the class this problem without any special efforts. What we have to find? Current. Current. How it arises? Due to change flux of magnetic field. So natural to use Faraday's law. That's what I wrote yesterday. That was first step. Second step. Electromotive force. What is it? Again, we have to know definition. What is it? Not letter. Not something mystical. It's a voltage of electrical field along path. Correct? And according to Ohm's law, for ring, not for arbitrary body, for ring, we know it's equal R resistance times current. We still don't know. And what about this expression? Oh, problem. We have two magnetic fields. One magnetic field caused by what? What at this point? Flux of magnetic field. Flux. When we say flux, we have to see this expression. It's a magnetic field times area surrounding by ring. Correct? But what creates this magnetic field? Current in transmitter and current in the ring. So two magnetic fields, primary and secondary, and two fluxes. Minus dF not dt, primary flux, minus dF secondary dt. So when you write down this term, easy, again, don't see number, don't see letter. Think what is it? What is it? Flux of primary field, which we do know, we solve forward problem. Now, so what is it? Magnetic flux of magnetic field through this ring caused by this ring. It's a secondary. So we obtain lovely equation. Unfortunately, that's only such simple equation. It's only one in our practice. Rest is solution forward problems, very complicated. Heat equations, boundary conditions, integral equations, finite matter differences. It's awful stuff. I only describe essence, but this example also allows to understand the idea where is the real difficulty. Resistance of the ring, we know, because we solve the forward problem. Current in the ring, we know. No, it's our goal to find out. This term, we do know, no doubt. Transmitter, we know current transmitter, size of the transmitter, we know where is our ring, forward problem. So this term now. What about this term? This is the flux caused by this current. So even unknown it's written here, unfortunately unknown also here. So unpleasant situation. In general we don't know, but that's the, as I told you yesterday, let's say the main key point why it's difficult to solve forward problems in electromagnetics. It's easy to solve forward problem in gravity. This flux is caused by this current. So in order to know in order to know flux, we have to know current. In order to know current, we have to know flux. So again, closed circuit problem. But fortunately for us, for the ring, we know something. We know we have one ring. If current changes twice, flux changes twice. If current decreases twice, this flux decreases twice. Why? Because there is Biot-Savart law, which tells field proportional current. In last century, famous German scientists discovered this coefficient proportionality. And they told Fs equal inductance coefficient proportionality times current. I substituted here, obtain equation for which contains only one unknown current. So, and what? That's what we got. A di dt plus Ri equal minus df naught dt. Let us compare first step with last step. No difference. This is Faraday's law. Now, if I now test your knowledge of this equation, what is the meaning of this term? Let us do it quickly because it's repetition.
Primary class.
Huh?
Primary class.
No, all this term. F not primary flux, but I am asking, what is it? You are speaking as mathematician. It does not work. You have to speak as physicist. What is it? So you have. That's our goal, to learn. Not to learn, but at least I will pay. I will pay attention this moment. Sorry? Correct. Electromotive force, which is created in our ring by only by primary field. Excellent. What is it with accuracy of sign? You see A, di, dt, but recall all meaning. What is it? Sorry?
It's a sign that is the one caused by the
Electromotive force.
Yeah.
Electromotive force with minus electromotive force caused by only body, which we usually don't know, but in the case of the ring we know relation with current. And finally, that's total electromotive force. You see? Very simple. If you forget about derivatives, about force, what is written there? Now, that's equation which we receive. Now, let us work with this equation, because ring again is very often extremely excellent model of conductor from physical point of view. So, last time we considered some special cases. It was only preparation. Now, two roles, time domain and frequency domain. So, model remains the same. Suppose current in transmitter changes in this way. Just a second. That's, I will take 0, that ramp time, that's time. So, you understand what I would like to do? I have current in transmitter. I have my ring, not necessarily horizontal. I draw horizontal, it could be vertical. Maybe it will not help us to detect, but arbitrary orientation. Now with R and L. No more Maxwell equation, simple equation, which I will write in the following form with your permission. di dt, I am looking for current, plus unit divide tau I minus unit divide RA df naught dt. Now what I did, I divided by L. By L. Correct? Now I introduce notation because Duncan spoke about this quantity today. So divide by this constant. What is the constant tau? It's only notation. L over R. Does it sound reasonable? Correct? So, now let us ask us what happens. This equation tells everything about our current induced in the ring. First of all, we will have current in the ring until this moment. But ring or body, transmitter, at the beginning current in transmitter constant. Will we have induced current in our body? Understandable why? No, current does not change, magnetic field does not change, so nothing will be there. Then current starts a rise. Current in transmitter starts decrease. Therefore, magnetic primary flux decrease. Therefore, electromotive force arises in the ring. So from this moment, induced current arises. True? Everybody follows me? Now, what happens later? What do you think? What would happen later? So, at the first, before, when current was constant, no induced current in the ring. Then during REM time, current arises. Why it arises again? Because flux changes with time. Faraday's law. Then I removed, completely torn off current in transmitter, took scissor, cut wire, and no more transmitter. That's the way. That's the best way, I understand. So the best way, so cut it, that sort of throw away. What happens with induced current in the ring? What do you feel? And then we will read equation. We will solve equation. What would happen? So during this time, induced current arises. Everybody understands? Only during this time there is a primary electrical field. Now, question, what would happen after? Current decays. Why it decays? Why it wants to decay? Or there is a case when it does not decay. Huh? So, your assumption, slowly, it's a good idea. So, first of all, you understand during REM time, from 0 to TR, current arises. That's clear. That's clear. Why it arises? Because change of the flux. Then, you are right, no flux through primary flux. No primary flux. You think that current instantly disappears. It must be reason. Everything what happens must have reason, at least in our geophysical profession. Maybe there are areas where it's possible to, something could happen without any reasons, but in our area, it's engineering area, must be reason. Could you give this physical reason why, if there is no primary flux, primary, I'm not talking total, primary, current must instantly disappear? So far, no physical reason. Now let us ask ourselves what happens with current, induced current, when transmitter shut off. No primary flux. So don't look in formulas. Now we are completely in physics. Now then we will force equation tell the same, exactly how we are thinking, not vice versa.
Because the flow of electrons will be impeded by the medium it's moving through, so the current will eventually dissipate by distant forces or something like that.
Oh, not like exactly. Electrons, current is a movement electrons. They are moving, they hit each other, They hit lattice, positive charges. So when they hit, there is a friction. When there is a friction, what appears? Heat. So electromagnetic energy transforms into heat. Certainly not instantly. It always takes time. So we must expect that current, our current in the ring, starts to decay. How decays, we don't know. We will find out. That's goal of formula. But formulas cannot tell us. Very often we can tell in general what happens without formulas. Formulas give us numbers. So in pores, in our rocks, ions is moving through pores. Without any doubt, they hit walls of the pore, each other. So always there is a friction. But of course, there is a special case, theoretical case, when there is no friction. Then you will be right. What is the case? Ideal conductor, superconductor. Then, if you create in superconductor current, then forever, simply forever, this current will be all time the same. Now we are ready to solve our equation. Understandable for everyone. Always, we don't know in all our methods case when it's not true. Now, let us solve this equation. First of all, can I write current equals 0 when t less than 0? Is it correct? When constant current was in transmitter, Faraday's law tells no electromotive force, no electrical field. No electrical field, no current. Then let us make jump. Let us find out what happens with current, induced current, when we measure at times which exceeds ramp time. That's where we measure. So let us be modest and don't try to find current within ramp time. We don't need it. So what happens with this equation? What would be how can we simplify this equation? Just a second. I would like to speak with mathematicians. Where are the girls from mathematical department? They left. One I see. So what happens? That's differential equation. What does differential equation mean? All quantities which are here are described behavior at the same time, at the same moment. So now I am interested time which exceeds ramp time. What happens with this step? We don't know. There is current changes with time. That's what we are looking for current. We don't know. What about this term? After ramp time. What is the value of the primary flux after ramp time? 0, because we cut by using scissors, our transmitter and no current. No primary current, no primary magnetic field, no primary flux. Logical. So instead, for times exceeding ramp time, when you completely removed your current and therefore primary flux, equation has the following form. I dt plus unit divide tau I equal 0. This is the simplest differential equation. That's the reason why I decided to bring it. It's only one problem which we will discuss, derivation. What is the solution of this simplest differential equation of the first order. Of course. So current at each moment when time exceeds RAM time is equal some constant E minus T over tau. Let us check me. Maybe I'm wrong. If we take derivative, what happens with this term? C over tau. And I take derivative. That's constant. That's variable. Take derivative. You will get minus C, correct? Tau exponent. What would be this term? Unit divide tau. C exponent equals 0. Of course, maybe I could take plus. No, plus does not work. Correct? So that's our solution. So we proved we didn't find our current, but we proved our assumption. What is our assumption? After RAM time, current behave as exponent. Now it's clear why parameter tau is called time constant. So far it's not clear. Now it should be clear. Why? Let me first of all to write L over R. The greater time constant, the slow decrease of the field. What does it mean, great time constant? It means conductivity is high. Oh, we are approaching to superconductor. Now, we increase dimension of our ring. Time constant, if you recall expression for resistance, for inductance, will grow up. So, the higher conductivity, the greater dimension, the greater time constant. We will use it when I start to discuss the ratio between useful signal and noise. Small conductor, resistive conductor, time constant becomes small. When time is equal time constant, signal decaying almost 3 times. Correct? That's why it's called, since tau characterizes rate of decrease of current, it's called time constant. It's a measure of rate of change of the field. Next. How to find this? We didn't solve problem. We don't know this constant. And now we are approaching to very important fact, which will bring us finally to concept of skin effect. So we know current here is 0. Then we don't know what is going on. And then it decays some exponential way with a known constant. Let us do the following. Let us try to find this constant. It's possible to find always, but let us pay attention one very special case, very practical. Let us assume that RAM time is very small. Let us assume that RAM time is small. We would like small RAM time. You sharply change current in transmitter. What happens with electrical field, primary electrical field? Very large. That's what we would like. We need large primary field because it creates stronger currents. If we will be lazy, make very large RAM time, I promise you for primary electrical field will be. Now, So let us look in our equation. So just a second. That equation is correct. Let me do the following. It's correct. Sum of these two terms equal primary electromotive force divided by inductance. Let me multiply time di dt times dt plus unit divide time I dt equal minus unit divide alpha too quickly df naught dt times dt. No problem. I only multiply by some time interval. It's a very simple arithmetics. Now I'm doing very physical procedure. Let me take integral from 0 to tau. From 0 to tau, not tau, I'm sorry, ramp time. T ramp, and T ramp. Again, I'm working with Faraday's law. I multiply time. I took integral from this equality within ramp time. And now I would like to ask you, what is the physical meaning of this quantity? First integral. So I don't know behavior of the current inside, but I took integral between 0 and ramp time. Pure calculus. Watch. Here two enemies which always kill each other. Integral and derivative. Now, could you tell me what is it? Current and ramp time minus current. Is it clear or not? Always integral from differential simply equal function, integrand. So I can write current and ramp time minus current at initial moment. Now, very simple arithmetics. No more this integral. Here we have plus, of course, plus. Let me leave this integral without any touch. Only our goal would be to understand what is it physically. What is here? Tau. That's tau. I'm sorry. What is here? Unit divide A, flux primary at 0 minus flux ramp time, primary flux, correct? Watch again, minus unit divide L, integral differential kill each other, and here flux 0 minus flux because I took into account minus. Now, please make me a favor, help me from physical point of view. Which term here is equal 0? Remember, it's induced current in the ring. Correct. This current was not yet induced. It's only moment when we started to decrease current. So we got induced current and the end of ramp time. I don't care how current changes, flux changes inside of ramp time. It's the iron rule, always correct. Ramp time, I'm sorry, not equal. plus this integral. I still write this integral. What is written here? Which term is equal to 0? At ramp time. So, very nice. We can write unit divide A, primary flux. Now, what is it? Can you help me? Again, physical approach. Current times integral from current during ramp time. What is it? Current. What physical meaning current? Number of charges which are going per unit time through cross section. Integral, what would mean? Total amount of charges which are going through our conductor during ramp time through any cross section. Is it clear? It must be clear. Now let us ask ourselves, what would happen when ramp time becomes smaller, smaller, smaller? First of all, what would be excitation in this case? Step function. So we can simply write I, ramp time, but we assume it's very small. What happens with this integral? If interval is tends to 0, no charges practically move. So this term is equal 0. It's equal unit divide L F naught. So we found at the end of any ramp time, as soon as it's small, current equal primary flux divide inductance. Now we are in good shape. If in the limit we assume ramp time is equal 0, we can simply write current at the first moment equal primary flux divided by L. Please remember our current which we found, C T tau. Can we comparing these two formulas to find constant? At the moment T equals 0, current must be equal constant. Therefore, this quantity, final result is current at any moment equal F naught over inductance T minus tau. And our small, very useful, as you see, problem is solved. Let us discuss it if you don't have questions. Let me plot graph C over tau as and current, induced current. That's transient response of the current, correct? Now, what would be graph of magnetic field caused by this current? The same Biot-Savart law. So it's also T over tau at any point, Z component for instance, it's the same transient response exponential behavior. There are always 3 stages of transient response caused by currents in conductor. 3. early, intermediate, and late. Now, if t greater than tau, that's start of late stage. If t less than early, essentially less, and everything between intermediate. 3 stages of transient response, at each, in general, not in the case of the ring, behavior of the field within early, intermediate, and late are different. Only in the case of the ring, all time exponent. But there is one more fundamental rule of in all possible cases, plate, sphere, chair, table, human bodies, buildings, any confined conductor. Confined, it means has finite dimension. If such conductor is located in non-conducting medium, or it's extremely resistive, that's the same practically, regardless of shape, dimension, at late stage, current and therefore magnetic field behaves as exponent. And nobody knows exception. Uniform conductor, non-uniform conductor, as soon as confined dimension, plate, dike, mile, 100 meters, doesn't matter. As soon as late stage arrived, transient field behaves as exponent. So this expression has some features rather universal as soon as we speak about late stage. Now there is another amazing feature, early stage. Let us look in this expression. What is what defines current at the first moment? Just a moment, I will explain what I would like to say. Our current in transmitter step function. Primary current. Now primary current create what? Primary magnetic field, primary flux. So if I have here ring, primary flux up to this moment equal F naught. Everybody understands? Constant, some number. Then I turn off current in transmitter. What happened with primary flux? Zero, disappeared. But what follows from this expression at the first moment? And this is fundamental fact, all theory of quasi-stationary electromagnetic field. At moment t equals 0, current is equal what? F naught divided by A. True? T equals 0, 1. Induced current only at the first moment. At the moment when you turn off, shut off your transmitter. Now, what is the meaning I naught times A? I naught, just a second, I will write better. I naught times A equal F naught. That's induced current, true? Induced current. So induced current at the first moment at such magnitude that if you multiply it by inductance, it will give you primary flux, which was before, not now. Now it's absent. You turn off current, no primary flux. True? Instead of primary current, you have induced current. But induced current so clever at the first moment that it does create such flux, because inductance times current is the flux through your body, which is exactly equal to primary flux. And this induced current does not know any other functions at the first moment at all. Only one requirement. It tells itself, I have to be so strong or so weak that my flux through my body must be exactly the same as before. And this fact this fact is physical basis of skin effect. About it we will speak after 6 months, so we'll come later. Clear? That's true again at very early stage for all conductors. We are not going to consider here, but it's true for all. Again, dike, plates, sphere, cylinder, earth. For example, in ionosphere, suddenly, very close to 70 kilometers, 100 kilometers, suddenly current shut off. Instantly, induced currents in the earth arise in such a way that flux through earth will be the same as before. You have a dike or body, who knows what is the shape, holes, what is important, confined. By the way, it's true not only for confined, for earth, for horizontal layer medium, as concerns early stage. Always turn off transmitter and induced current arise such magnitude and distributed in such clever way that flux will be the same as before. Now, do you have some questions? If not, I will continue. Please.
Can I go back just a couple of steps when you ignored or maybe dismissed that term working out?
I understand. Just a moment. I only try to write it correctly. Current. Just a second. Just a second. Becomes worse pink. So we have first term, integral from 0 to tau, correct? Di dt plus unit divide tau, integral from tau I dt. That's term I'm going to neglect. And equal minus unit divide L, integral tau, not tau, it's rem time, all the same miss. And df not dt. So we are talking about this term. Please.
With switch off at a very, very small time, doesn't the BDT go to infinity?
If you do ideal, that's what you don't have right to do. Faraday's law does not work in the form which we wrote for ideal step function. Faraday's law is minus df dt. I didn't mention, I thought I will mention somewhere in this time. This Faraday's law, beautiful classical Faraday law, does not have any meaning in this form, for cases when current mathematically shut off, step function. whose derivative is equal infinity. What I am doing, I don't take REM time equals 0. I consider extremely small REM time. Then it works.
Doesn't current, well, dVdt go towards infinity, and likewise
Just a moment. I don't see here here current times.
I'm just thinking the current goes towards infinity, and then you're having time go towards 0 and multiplying.
No. Just a second. Not current goes to infinity, but electromotive force. It's a completely different quantities.
But isn't current related to the electromotive force?
Related, but it's not as directly proportional. Yes. No. So if you that's the fact. So when you decrease REM time, very well, you increase primary electrical field. Primary. But instantly secondary arises, which is directed opposite and does not allow you to total field go to infinity. And that's what is written here. It tells you when you make very sharp turn off, your current is not going to infinity. I would say this equation is analogy of Faraday's law when you have ideal step function.
Alex, I think that the point that he's making is that as the time of the ramp gets very small, the EMF gets very large, but it
Primary.
is of large amplitude, but it acts for a very short time, and the actual initial current in the target is the product of the area under that curve.
But that comes from here.
EMF times delta T, so that as the EMF goes up and the delta T goes down, the area is still the same. So as Alex
But
says,
this geometrical model, there is no physical law which tells everything is defined by area times magnitude. It's consequence of this fact.
Alex, I look at it from an electrical engineering point of view.
I see. So that's what happened. Now, is it necessary to have ideal step function? No. Let us look in this expression. Well, this expression. This is that's value of the current at the first moment if you have step function. Correct? But let us forget about step function. Let us take real case, REM time. If time of measurement much smaller than time constant, exponent will be equal 1 because t less than tau constant. So it's all this consideration is true at the first moment as soon as REM time is smaller than time constant. Now let us stop here. Yes, I watch for time.